Hello class, this is Ms. Riggins with today's video on section 8.5, Polar Coordinates. As you're watching the video, please remember to write down notes, including important information, statements, equations, formulas, or graphs. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. At the conclusion of watching the video, write a brief summary about what occurred in the video in your notes and submit that summary as well as a top question via the online whisk form. All right, let's begin. We're actually going to do a new unit or new section on polar coordinates that involves trigonometry. So here we have, as an example, a point on a Cartesian plane, and we are used to identifying that point in coordinates of the x and the y, where x represents the horizontal distance from the origin and y represents the vertical distance from the origin. But another way to represent it is using, instead of x and y to represent horizontal and vertical coordinates, we use instead r and theta, where r represents the distance from the origin to that point, and theta represents the counterclockwise angle that the line segment makes with the x-axis. Okay? And so to convert between polar and Cartesian coordinates, we basically use this expression, which is r cosine theta is the x value, and y is equal to r sine theta, which is the y value, which makes sense because if this was the unit circle, the cosine of this angle would be the horizontal distance and the times the radius. Yeah, the radius times the cosine of the angle would be the horizontal distance, and the radius, i.e. the hypotenuse of the triangle, times the sine of the angle would be the vertical distance. Okay, and the relationship between x and y and r is that r is the distance using the distance formula. In other words, it's x squared plus y squared, and the square root of that is r. And to figure out the angle from x and y, we can use the tangent, inverse tangent for y divided by x, but sometimes that doesn't always work, especially if x is equal to 0. So then sometimes we have to use the cosine, inverse cosine, and the inverse sine to make sure we get the right angle. And these are the formulas for that as well. Very similar to what we were doing last class, okay? Now let's take a look at an example. So given the Cartesian coordinates for the points with polar coordinates. So in other words, here are the polar coordinates. Now we have to determine the Cartesian coordinates, the x and y. So again, x is equal to r cosine theta. So in this case, our r is 7 and our theta is pi over 3. So the x value is 7 times cosine of pi over 3, which ends up being 7 times 1/2, 7 halves. And the y value is r sine theta, and then we get y is equal to 7 square roots of 3 over 2. So we have our x and y coordinates as 7 halves and 7 square roots of 3 over 2 for the same point in the polar coordinates. Now, if I give you the polar coordinates, if I give you the Cartesian coordinates, what are the polar coordinates? So then we would use a relationship that the radius is equal to the square root of x squared plus y squared. So we get the radius is 5. And that the tangent of the angle is the ratio of the y value divided by the x value, 4 divided by 3. And in this case, for tangent is positive in the first quadrant, and so we end up with 53 degrees. Now, if tangent was negative, then we would have a different situation, and we'll take a look at examples of that in class. All right, so very simple. Now, fortunately or unfortunately, interestingly enough, there's always more than one set of polar coordinates for a point. Unlike in a Cartesian plane, there's only one set of coordinates for a point. So let's take a look here at this example, in this point right here. And if you haven't noticed, the circles represent the circles with different radius. So this is radius 1 circle, radius 2 circle, radius 3 circle, radius 4 circle, okay? And that's usually how it is. And so here we have this point here that's on this line. And so the question is, what are the coordinates for this point? Well, the radius is 3 because it's on the 3 circle. And the angle that it produces is the pi over 4, and that's because, as we can see here, it's on the line. That's where represents a pi over 4 angle. Okay, but so anyway, I can say that the coordinates are 3, pi over 4, the polar coordinates. But then I could also add 2 pi to the pi over 4 and get an angle of 9 pi over 4. And then we would end up with these polar coordinates for the exact same point. And I could do this instead of adding 2 pi, I could subtract 2 pi, and I'd end up with these polar coordinates. So I know some of you are saying, well, what's the right answer? Well, they're all right, but normally we tend to look at angles that are between 0 and 2 pi when naming polar coordinates, because of the continuous nature of a circle, we could keep playing this game over and over and over again. So generally from 0 to 2 pi is where we would like our theta to range to be when we're identifying polar coordinates, okay? Now let's talk about graphing equations. Now if I were to graph the line of radius equals 1, well that would just be, radius equals 1, that would just be the circle here. If I were to graph because I don't specify the theta, it can be any theta, and so that would be that circle. If I want to graph the line radius equals to 4, then I would graph, it would be this circle, because here on every point on this circle has a radius of equal to 4. But if I want to graph the equation radius is equal to theta, we call those type of equations, polar equations, Archimedean spirals, okay? And without graphing, just taking a look at the values, if I were to say, well, if the radius is equal to the same length as the angle rotation, I can see that as the radius increases, of course, so does the angle rotation. And these are what the values look like. If I want to convert the angles from radians to degrees and the radius from in pi over 6 notation or pi formation to approximate value, I would get something that looks like this. So the question is, how can we graph it? Well, we're not going to actually be graphing by hand polar graphs, okay? But I'm going to show you in the calculator how you can graph that. If you go to the graphs page in the calculator and you go to menu and you do graph entry, you're going to see an option for polar. And when you do the polar coordinates, as you can see right here, what you're going to end up with is kind of looks like a piecewise equation, where the first piece is actually what is the equation for the radius as well. And then the second part actually about the range for the theta. Okay, so if I want to do over here just theta, I'm going to hit the symbol button and just type in theta, and I press enter. I get this, which is an Archimedean spiral. Okay, so moving on, and as we can see here, as the values gets bigger, the values of the angle gets bigger, the values of the radius gets bigger, or R value, and it looks something like this. Okay, another type of graph that you should be aware of is what's called roses, and it looks of this form. For any integer n, if r is equal to a times sine of n theta, or r is equal to a times cosine n theta. Okay, where a will kind of represent how wide the rose is, and n theta will tell you how many petals there are. So let's do an example. Let me go back up here and do my graph entry. I don't know why I just did that. I could have just went up here. I'm actually going to look at this. I'm going to do 2 times cosine of, let's see, 2 theta. And we get, again, a rose with 4 petals. They call these petals. And if I were to increase 3, and we can do this with sliders really easily in class, the petals get bigger. And if I want to increase the number of petals, decrease the number of petals, I change the b in the cosine value. Okay, so the thing you should be able to do is recognize that there are rose petals that these are roses of this form, okay? And here's an example of some, okay? The next type of graph is called limicons, and I don't know how to pronounce it because I'm not French. But they kind of look like rose forms, but they add a constant to it. So I'm just going to add a constant very quickly to this. Oops. Okay, and it looks like that. Those are called limicons. Okay, in this case, the period is just 2 pi. Well, there's no b value. The b value is just 1. All right. Can we graph inequalities in polar coordinates? Yes, you can. We're not actually going to do it, but I want to give you some examples that your book gave. If I want to graph the inequalities of this CD cover, well, in this case, the radius of this little small circle is 7.5, and the radius of this big circle is 60. Okay, so as a result, I can say as long as my radius is in between 7.5 and 60, I will end up with the interior of the CD cover. Okay, and theta can be any value between 0 and 2 pi. So any of those combination of points that fit these polar coordinates, where r is between 7.5 and 60, it works. Over here with the 18-inch pizza, that means the radius of the pizza is 9 inches. Okay, and if I cut the pizza into 12 slices, then 12 into 2 pi is pi over 6. So we have the radius can be any value in between 0 and 9. And the theta has to be any value between 0 and pi over 6. And then you'll get this interior.